sklearnensembleExtraTreesRegressor. Description: ExtraTreesRegressor is an ensemble learning method for regression that operates by constructing a multitude of decision trees during training and outputting the mean average prediction of the individual trees. Each tree is built using a random subset of features and data points, leading to a diverse ensemble. This randomness helps in preventing overfitting, making ExtraTreesRegressor robust to noisy data. Inputs. X. This is the input feature matrix, where each row represents a data point and each column represents a feature. The values in X can be numerical or categorical. Y. This is the target variable that the model aims to predict. It is a one-dimensional array containing the values for each data point in X. Outputs. Predictions. The model outputs a prediction for each data point in the input feature matrix X. These predictions represent the estimated values of the target variable based on the trained model. Steps. Tree construction. The model constructs multiple decision trees, each using a random subset of features and data points from the training set. This randomness ensures diversity in the ensemble. Prediction. Averaging. During prediction, each tree in the ensemble makes a prediction for the given data point. The final prediction is the average of the predictions made by all the individual trees. Metrics. Mean squared error. MSE measures the average squared difference between the predicted and actual values. It's a common metric for regression tasks, emphasizing larger errors. R squared represents the proportion of the variance in the target variable that is explained by the model. A higher R squared value indicates a better fit. Visualization plots. Feature importance plot displays the importance of each feature in the model's predictions. This plot helps identify the most influential features. Partial dependence plots visualizes the relationship between a specific feature and the predicted outcome, while holding other features constant. It helps understand how changes in a feature influence predictions. Fine-tune parameters. Nestimators controls the number of trees in the ensemble. Increasing this value often improves performance, but can increase computation time. Max depth limits the maximum depth of individual trees, preventing overfitting. Deeper trees can capture complex relationships but risk overfitting. Minsample split. Minimum number of data points required to split a node in a tree. A higher value prevents overfitting to small groups of data points. Max features controls the number of features randomly selected at each node split. It helps in diversifying the trees and reducing variance. Uncertainty methods. Bagging. By randomly sampling data points and features for each tree, the model implicitly captures uncertainty. The variance in predictions across the ensemble provides an indication of uncertainty. Confidence intervals. Depending on the implementation, confidence intervals for predictions can be calculated, quantifying the range of possible values with a certain degree of confidence. Challenges and fixes. Challenge 1. Overfitting occurs when the model learns the training data too well, resulting in poor performance on unseen data. Sample use case that resulted in challenge 1 using a large number of trees, nestimators and a high maximum depth. Max depth without sufficient data can lead to overfitting. Fixes to challenge 1. Reduce the number of trees, nestimators. Limit the maximum depth of individual trees. Max depth. Increase the minimum number of samples required to split a node. Minsample split. Consider using techniques like cross-validation to evaluate model performance and prevent overfitting. Challenge 2. High computational cost. Building a large number of trees can be computationally expensive, especially with large datasets. Sample use case that resulted in challenge 2. Training a model with a high number of trees. Nestimators and a large dataset can take significant time. Fixes to challenge 2. Reduce the number of trees nestimators. Consider using parallel processing techniques to speed up training. Optimize the hyperparameters to reduce the number of splits and nodes in the trees. Explore alternative algorithms like random forest, which may have a faster training time for similar performance.